Hi, hope you are all doing good. This is the second session of Module 4 Random Processes. In the first session, we have seen what a random process is and what are its classification, and certain real world examples were also discussed. I think students who study electronics are dealing with signals, and there it happens that a receiving signal at the receiving end may not always be the same as it was transmitted, right? So due to some noises, their amplitude may be different, their phase shift may be different, or their frequency may be different. So there comes the importance of random signals. Okay, so as an example, if x of t is a random process, and we define this as a sine omega t plus phi, and here this one is a function of t, time. A is the amplitude, omega is the frequency, and phi is the phase shift. So for a signal, if a the frequency, omega, and phase shift, if all these three are constant, that means they are deterministic values, then always you will get a fixed value for each t, right? But it's not always true that a will be deterministic. Sometimes when we receive a signal, the amplitude of the transmitted signal may not be the same as the amplitude of the receiving signal. That may be different. So this amplitude can be a random variable, and this frequency can be a random variable, and this phase shift also can be a random variable. So that means this one, if any of these three variables, a, omega, and phi, are random variables, I mean any one or more are random variables, then this one becomes a random process, right? So that is why I think this topic is included in the electronic syllabus, because they deal with signals more, right? Okay, so in this module, in this session, we are going to see special classes of random processes, certain based on certain properties of random processes. We are going to see some classes of random processes. For example, I'll write some classes of random processes here. So first one, stationary process. Stationary process. And the second one, wide sense stationary. Wide sense stationary process. Then Poisson process. Then Markov chain. Then Markov process. Renewal process. Then pure birth process. then birth and death process, and so on. So these are all special classes of random processes. Not only these, there are a lot more. Uh, so in this module, that means in module, actually we are discussing now module 4, right? So in module 4, we are going to discuss only these two kinds of processes, like stationary process. This one has certain very strong conditions, so dealing with stationary process is not so easy. So with some relaxations, we will see what are wide sense stationary process and its properties. Okay, so we'll concentrate wide sense stationary process in module 4, and that's all we will study in module 4. Okay, wide sense stationary process and its properties. And then in module 5, we'll see two different random processes. One is Poisson process and another one is Markov chain. So we define these two processes. I mean, what are their special properties? Based on that, we'll do we'll derive certain formulas and we'll do some problems. Okay, that's all we will see. And these one are certain process, but these are just out of the scope of our syllabus. If you are interested, you can go through it. Okay, you can refer some textbook and all. You can go through it. Okay, so these are the special classes of random process. Now in this module we focus on this stationary and wide sense stationary process. Now let's go to the definition of a stationary process. So stationary process. So let x of t be a random process. Let x of t be a random process, and let f of capital F is a distribution function, and this is not just the distribution function, but we define a general nth order distribution function, that is f of x1, x2, etc. xn, t1, t2, etc. tn. And this means that, see, a random variable is x of t, and this one represents the probability that x of t1 is equal to x1, and x of t2 is equal to x2, and x of t3 is equal to x3, etc. x of tn is equal to xn. That means at each ti, the probability that x of ti is equal to xi, and this one is a joint distribution. Okay, and let this be the distribution function. Then we say that this x of t is a strict sense stationary process. Strict sense stationary process. In short, we write this as SSS, strict sense stationary process. If this distribution function satisfies this condition, f of x1, x2, etc. xn, t1, t2, etc. tn will be the same as f of x1, x2, etc. xn. And now each of these time epochs, t1, t2, etc. tn, are shifted to a particular toy units. Okay, so this t1 becomes t1 plus 2 and t2 plus 2, etc. Tn plus 2, right? Okay, so actually it means that if we shift the time epochs t1, t2, etc., tn to tau units, then again you will get the same distribution function. Okay, that means it is invariant under a particular time shift. Okay, such processor are called stationary process. Though this condition seems to be simple, this one has a very strong correlation between these random variables x1, x2, and etc. xn. Okay, so see, at least two of the implications are, so if x of t is an SSS, then these two conditions will be satisfied. That means if x of t is a stationary process, then its expectation, this is the first condition, expectation of x of t will be a constant. This is the first condition you will get. Expectation of x of t will be a constant. And the second condition is going to be that is about the autocorrelation r of t1 and t2. R of t1 and t2. And this will be a function of t1 minus t2. And if t2 minus t1, assume that t2 is greater than t1. So this will be a function of the difference of these two times. And if we denote t2 minus t1 as tau, we represent that as t of tau, where tau is t2 minus t1. Okay, so if x of t is a strict sense stationary process, or SSS, then x of t has these two properties. E of x of t will be a constant, and r of t1, t2 will be a function of r of t2 minus t1. Okay, now it's not easy to prove that a given random process is strict sense stationary, because this is not easy to prove this condition. Okay, so we mainly focus on these two conditions. That means we check whether the expectation is a constant and the autocorrelation function is a function of tau. Okay, so if a random process satisfies these two conditions, we say that x of t is a wide sense stationary process. Okay, so there comes the definition of wide sense stationary process. Okay, so this is a definition: wide sense stationary process, WSS. So let x of t be a random process, then x of t is said to be a wide sense stationary process if it satisfies expectation of x of t is equal to a constant, and autocorrelation function is the difference of those two time epochs, t2 minus t1, or r of 2. Okay, so that's all about the definition of a wide sense stationary process. Now we can, based on these definitions, we can move on to some problems. Okay, now okay, this is the first problem. Show that the random process x of t is equal to alpha cos beta t plus phi is wide sense stationary, where alpha and beta are constants and phi is a uniformly distributed random variable in 0 to 2 pi. Okay, so here this random variable is explicitly defined as a function of t, and here we have three parameters alpha, beta and phi, and it's given that this alpha and beta are constants and this phi is the random variable. and if this phi is again a constant, then this is not a random process, this is just a function of t. And since this phi is a random variable, uh, this one becomes a random process. Okay, so to prove that this one is a WSS, two things have to be proved. First one is that we find the expectation of this one, and that should be a constant. Second one, we find the autocorrelation function, at autocorrelation function at t1 and t2, then we will get a function of t2 minus t1. Okay, so first thing, we find the expectation of x of t. Expectation of x of t. So this is expectation of alpha cosine of beta t plus phi. Okay, alpha is a constant, this is not a random variable. That means this one is a fixed quantity, so its expectation is always that value itself, because there is no randomness here. So alpha comes out, and this is expectation of cosine of beta t plus phi. Now in this function you can see that expectation of, if it is just expectation of phi is a uniform distribution, we know the formula of the expectation of a uniform random variable. We have seen in the second module. But here it's not just phi, but this is a function of phi. So what we are supposed to do is, first we find the density function of phi. Okay, so it's given that phi is uniform, therefore its density function f of x is equal to 1 by, the formula, it's a uniform distribution defined in an interval AB. So its density function will be 1 by b minus a. So it's 1 by 2 pi minus 0. Okay, x belongs to 0 less than x less than 2 pi. All right, so here, so it's alpha times, and the formula is to find the expectation of this one, integrate the function. Actually, if see, expectation of x is nothing but integral x times f of x dx, right? We have seen this formula, and that is just expectation of x. Here it's not just x, but a function of x. So it's enough to substitute the complete formula here. So it's cosine of beta t plus phi times its density function. Density function of phi is 1 by 2 pi times dt. Okay, times you have to integrate that with respect to the variable t from 0 to 2 pi. Okay, all right, so interval 0 to 2 pi cos bt plus phi times its density function times, here the random variable is phi, so it's not just t but phi, d phi. Okay, so 1 by 2 pi is a constant, so alpha by 2 pi integral of cosine theta sine of beta t plus phi. We are integrating with respect to phi, so it's just sine of beta t plus phi. Apply the limit from 0 to 2 pi. So you'll get alpha by 2 pi sine 2 pi plus beta t minus sine beta t. And here sine is a periodic function with period 2 pi. So sine of 2 pi plus beta t is the same as sine of beta t. So the answer is sine of beta t minus sine of beta t is equal to 0. So that is expectation of x of t. And note that this is a constant. This is a constant. So the first condition is satisfied. First condition is satisfied. Now we find the second condition. That means we need to find the autocorrelation function. Okay, so autocorrelation function R of t1 t2 is equal to, its definition is expectation of x of t1 times x of t2, which is equal to expectation of, substitute this one, x of t1. This is x of t, so replace t by t1. Alpha cos beta t plus phi times beta t1 plus phi alpha cos beta t2 plus phi, and alpha times alpha square comes out. So alpha square times expectation of, this one is cos A cos B, right? Cos A cos B. So we can use a trigonometric result here. Cos A cos B is cos A plus B plus cos A minus B, cos A minus B. Okay, this is what you will get. So alpha square times, and here we have a theta plus theta, it's 2 theta, and here there is no function of theta. So it's enough to take the expectation of only the first term, because that contains theta, this one doesn't contain theta. So this one will be a constant. Okay, so the first part will be expectation of cosine of beta t1 plus beta t2 plus 2 theta plus, and no need to take the expectation over here because this is a constant. So it's just cosine of beta times t1 minus t2. Okay. Now, as in the previous case, we can find the expectation of this one using an integral. Integral 0 to 2 pi, the whole function, cosine of beta t1 plus beta t2 plus 2 theta times the density function of theta is 1 by 2 pi d theta plus this function, cosine of beta times t1 minus t2. Okay, and the same procedure we can integrate this one. It's cosine, integral of cos is sine. Okay, we can apply the limit 2 pi and 0. So this one will be 0, as we have seen in expectation of x of t. This one will be 0, and the final answer is going to be equal to alpha square times, this one will be 0, and this is cosine of beta times t1 minus t2. Cosine is an even function, so t1 minus t2 is the same as t2 minus t1. Okay, so if we denote t2 minus t1 as 2, this will be cosine of beta 2. Okay. Now we have proved two things. The first one, expectation of x of t, we got as 0, which is a constant, and the autocorrelation function r of t1 t2, we have proved that, which is a function of t1 minus t2 or t2 minus t1 here, because cosine is an even function, so we can write this as t2 minus t1. Okay, so those two conditions are satisfied, therefore x of t is wide sense stationary. This is that problem. Okay. Okay, this is our second problem. And here again, x of t, this random process is defined explicitly as a cos lambda t plus b sin lambda t. A and b are wide sense stationary. Lambda is a constant. And a and b are random variables. And these are the conditions of A and B. Expectation of A and expectation of B are 0. Expectation of A square and expectation of B square and expectation of AB are all 0. Also, it's given that A and B are independent random variables. A and B are independent random variable. So, the first condition, we have to find expectation of x of t. So, it's expectation of a cos lambda t plus b sin lambda t. A and b are random variables. Cos lambda t and sin lambda t are deterministic values. So it's enough to take the expectation of only random variables. So expectation of A times cos lambda t plus expectation of B times sin lambda t. It's given that expectation of A and expectation of B are 0. So the answer is going to be 0, which is a constant. Okay, so expectation of x of t is a constant. So the first part is proved. Second part, we find the autocorrelation function r of t1 t2. The definition is expectation of x of t1 times expectation of x of t2. So it is expectation of, substitute x of t1, a cos lambda t1 plus b sin lambda t1 times a cos lambda t2 plus b sin lambda t2. Now you multiply all these together, and first when you multiply you will get a times a square cos lambda t1 cos lambda t2, and when you take the expectation you will get expectation of a square cos lambda t1 cos lambda t2 plus next one ab. So expectation of ab, so expectation of ab times cos lambda t1 sin lambda t2 plus, now the third time, these two, ba, so expectation of ba times sin lambda t1 cos lambda t2 plus, and the last two times expectation of b square sin lambda t1 sin lambda t2. So when you multiply you will get 4 times. and it's enough to take the expectation of only the random variables. And all these values are given. Expectation of a square is 0, expectation of b square is 0, expectation of ab is 0. Since a and b are independent, expectation of ab and expectation of b are all 0. So here when you substitute all these values, you will get 0. And here the autocorrelation function is again 0, right? Or actually there is a small correction in the problem, that is expectation of a square is equal to expectation of b square. That's all it's given. Expectation of ab is equal to 0. Okay, so at the end, expectation of a square and expectation of b square are the same. So these two terms will be 0. Expectation of ab is equal to 0 and expectation of ba will be 0. So since these two are the same, can write expectation of a square, these two are the same. Okay, so that takes out and you will get cos lambda t1 cos lambda t2 plus sin lambda t1 sin lambda t2, right? So this is expectation of a square times, and this is cos A cos B plus sin A sin B, nothing but cosine of lambda t1 minus lambda t2, or lambda times t1 minus t2. It's again a function of t2 minus t1. Right? So this one is a function of t2 minus t1. And cosine is an even function, so t2 minus t1 and t1 minus t2 are the same in this case. Okay, so here again two conditions are satisfied. Expectation of x of t is 0 and the autocorrelation function is a function of 2 or t2 minus t1. That means x of t is wide sense stationary. Okay. Okay, this is the third problem. The process x of t belongs to the index at t, whose probability distribution is given as probability that x of t takes the value n. So these are the probabilities. That means here the random variable x takes the values n. N varies from 0 to infinity. So when n equal to 0, its corresponding probability is given, at by 1 plus at. When n is equal to 1, substitute n is equal to 1 here, you will get the probability. N is equal to 2, substitute n equal to 2 here, you will get the probability. So instead of giving x of t as an explicit relation, here we are given the probability distribution of this random process. Probability distribution of random process. So if we are given such a probability distribution, how can we calculate expectation and autocorrelation functions? And that's what we are going to see. Okay, here the question is, show that x of t is not stationary. X of t is not stationary. So from the definition, proving that a random process is not stationary, we have to calculate the distribution function and we have to prove that it's time invariant or it's invariant under translation of time. But that may not be possible always. As I have mentioned earlier, that process is difficult. So here what we do is we find the possible statistical quantities like expectation, the second moment like e of x of t the whole square, or the autocorrelation function, or the variance, whatever we find, if any of these are functions of t, if any of these are functions of t, then we can say that that is not stationary. Okay, so that is what we are trying to do here. So first we find expectation of x of t. Okay, so actually x of t is a random variable, right? For a fixed time, x of t is a random variable that takes values from 0 to infinity. So we have seen it's a discrete state space continuous time random variable. So to find its expectation, we know it's sigma n times its probability. So n takes the values from 0 to infinity. So n times Pn. Okay, substitute Pn. So when n equal to 0, you know this one will be 0. We don't need to consider that. Okay, so n times at all raised to n minus 1 by 1 plus at all raised to n plus 1. Substitute the values of n. When n is equal to 1, you will get this. N equal to 2, you will get this. N equal to 3, you will get this. And from all these terms, it can be seen that 1 by 1 plus 80 the whole square is common. 1 by 1 plus 80 the whole square is common. Take that out, and it remains 1 plus 2 x plus 3 x square plus etc. And this one has a standard expansion like 1 plus 2x plus 3x square plus etc. is 1 minus x the whole raised to minus 2. 1 minus x the whole raised to minus 2. Take the LCM, 1 plus 80 minus 80, 80 will be cancelled, and then 1 by 1 plus 80 the whole square times 1 by 1 plus 80 the whole raised to minus 2. These two terms will be cancelled and the answer is 1. So this is what the expectation. Now see, this is a constant, right? So we cannot say anything right now. We cannot say anything. So we now we try to find expectation of x of t the whole square. Expectation of x of t the whole square. Let's see that. Okay, now e of x of t the whole square. And here expectation of x square we need to calculate. So this is a formula. This one also we have studied earlier. Sigma n square p of n. And here we do an adjustment. We write n square as n times n minus 1 plus n. Okay, the same kind of adjustments we have done in finding e of x square of binomial distribution and Poisson distribution. The same kind of adjustment here. So you substitute p of n here. This is what the expectation of x of t, and that is 1. We have just seen that. Now substitute n equal to 2, 3, 4 and all. Okay, and from these terms you can take 80 by 1 plus 80 the whole cube out. So in the first term it remains only 2. The second term it remains 3 times 2 times 80 by 1 plus 80 and so on. The last term plus 1. And this expansion is 2 times 1 minus x all raised to minus 3, and that is what this expansion is. 2 times 1 minus x the whole raised to minus 3. And when you simplify this one, 1 minus 80 plus 80, it will get cancelled and it remains as 1 plus 80 the whole cube. So this will be cancelled. So the answer is going to be 1 plus 280. And this is a function of t. This is a function of t. Okay, so expectation of x of t the whole square is a function of t. It means that this is not a stationary process, because you know that expectation or the second moment depends on time. That means this is not a stationary process, but this is an evolutionary process. Okay, so not a stationary process. So x of t is not a stationary process. All right. Okay, so we have seen 3 problems from this section. Some more problems are there. We'll see that in the next session. Okay. Thank you.